We've learned that when a wave encounters a boundary between two materials, we're always going to get some reflection, which means bouncing back, and we're going to get some transmission, which means it keeps going. Some of it's going to keep going, some of it's going to be reflected. We know that sometimes most of it will be reflected with only a little bit transmitted, and sometimes most of it will be transmitted with only a little bit reflected. Well, it all depends upon what the nature of the materials are as to how much gets reflected and how much gets transmitted. Let me cover this up so you can't just cheat. If the materials are very, very similar, then we're going to get more of what? Reflection or transmission? Yep? Good. We're going to get more transmission. You think about that. If the materials, the wave is going from one material to another, and the materials are almost the same, well, then most of the wave is going to keep going as if it never encountered a boundary, right? And then you're going to get a little bit reflected, just a little bit reflected in that case. But if the materials are very, very different from one another, then you're going to get mostly reflection with only a little bit of transmission. Now, if we look at the part that's reflected, we know that some of that wave, that part of the wave that's reflected, then that wave will be reflected either right side up or upside down. Who can tell me when it's going to be reflected right side up? There's two kind of things that we looked at there. It's reflected right side up when. Picture the demonstration that we did in class and in the atrium. When was the wave reflected right side up? When Jack was holding on to the slinky in the classroom here on the floor, or when the slinky was just going to the air in the atrium? When did it reflect right side up? Yeah? In the atrium, right. So that means it's going to be reflected right side up when it's going from more dense slinky to less dense air. In other words, when it's not attached. Right? It's reflected right side up when it's going from more dense to less dense, or when it's not attached at the end. So that means it's going to be reflected inverted in the classroom, right? When Jack was holding on to the end of it. When it's going from less dense to more dense, or when it's attached at the end, then it's going to be reflected upside down. Finally, the law of reflection. Okay, this occurs when we have a wave encountering a boundary at an angle. Not just straight on, but at an angle. We know that some of that wave is going to be transmitted, and some of that wave is going to be reflected. The part that's reflected might be right side up, or it might be upside down, depending upon the nature of the materials. Which one's more dense, which one's less dense. But the part that is reflected, whether it's right side up or upside down, will always be reflected at the same angle that it struck it at. But be careful. We don't worry about this so much in Physics 20, but we look at it a little bit deeper in Physics 30. We always have to measure that angle, not from the boundary, but from this dotted line right here. What do we call that dotted line? You guys remember what we call that dotted line? I'll give you a hint. It's 90 degrees to the boundary. If we look at our imaginary physics thesaurus, book that has words that mean the same thing as other words, what would we see beside 90 degrees? What physics word would we see beside 90 degrees? Sorry? Right angle, sure. That's more of a math term, but what do we usually call 90 degrees in physics? Yeah, it's perpendicular, sure. Those are both math terms, and we use those for sure. Normal, right? Remember the normal force was the force that was at 90 degrees to the floor or to the track or whatever. The normal line is an imaginary line that's drawn at 90 degrees to the boundary. So 90 degrees absolutely means perpendicular, absolutely means all these other things. But in physics, it's 90 degrees is synonymous with normal. So this is a 90 degree angle we have with the boundary. We call that the normal line. And our angle of incidence, theta I, or you could call it theta 1. I think we called it theta 1 yesterday, actually, didn't we? Doesn't really matter. Is equal to the angle of reflection, which we could call theta 2 as well, as measured from the normal line, or that line that's drawn at 90 degrees to the boundary. Well, next we talked about transmission, the part of the wave that keeps going. We look at the part of the wave that keeps going. Remember, it's not all the wave. We're always going to get some reflection, maybe only a little bit of transmission, maybe a lot of transmission, but whatever. We're looking at the little bit or the lot that is transmitted. What two properties will always change? Which two properties will always change when the wave is transmitted or when the wave keeps going? Yeah, Erica? Good. The speed and the wavelength will always change. We're going to circle those, group them together. Which property of the wave will sometimes change when the wave goes from one medium to another, when the wave is transmitted? Which one can change but doesn't always? It depends upon how the wave strikes the boundary. Luke? It would be the theta, yeah, the angle, the direction. So we'll kind of list that separately. And which property of the wave doesn't change no matter what? Whether it strikes it straight on or it strikes it at an angle, the part that's transmitted will always keep the same what? Good. The frequency, once a wave has been produced, always remains the same. Make sense? All right, I'm pretty sure. Now, don't quote me on this. I'll take a look at your final exam before next Friday, before the last day of classes, and we'll go through a few things, and I'll give you a few hints on it. But I'm pretty sure there's one of your multiple choice questions that basically asks you what I just asked you. Okay, which properties change and which properties stay the same. And I can't remember exactly how I ask it, but it's pretty much the same thing, I think. I'm pretty sure that that's on there. There's, I want to say there's 25 multiple choice questions on the exam, and like maybe 11, I want to say, written questions. But like I said, before next Friday, before the last day of class, I'll pull the exam out and be a little bit more specific, a little bit more clear on exactly what to expect there. All right? Good. Well, what else did we do yesterday as well? We talked about interference. When a wave strikes another wave, we get a combination of waves. Sometimes we get a bigger wave. We get a bigger wave, like when two crests hit each other. Then what do we call that? What kind of interference is it, Erica? Good. It's constructive interference. If we get a bigger wave because two troughs hit each other, then we call that? No. Nope. If we get a bigger wave because two troughs hit each other, we still call it constructive interference. Okay, that's a pretty common mistake, actually. We got two crests hit each other. Everybody knows, well, you're making a bigger crest, right? You're constructing something. It's constructive interference. If two troughs hit each other, you think, like, well, we're digging a hole. We're digging a deeper hole. That's destructive interference. No, it isn't. Okay, if you're digging a deeper hole or making a bigger wave, that's still constructive interference. You're still constructing a deeper hole. Okay? Whenever you get a bigger wave than you started with, that's constructive interference. But you get a smaller wave than you started with when a crest and a trough meet each other, we call that one destructive interference. We know right now when we look at this that we're going to get constructive interference. Right? Constructive interference because a crest meets a crest. Doesn't matter which way they're going. At this moment in time, hey, these two waves overlap, they're both crests, we're going to get constructive interference. The way we determine what this wave looks like, the interference pattern looks like, is to do a little bit of adding. The ends here, those are pretty straightforward, right? So let's focus on the middle here. If we add together the first wave, which is 2 blocks above, and the second wave, which was 1 block above, then we're going to get 3 blocks above. 2 blocks and 2 blocks gives me 4 blocks. 2 blocks and 2.5 gives me 4.5, and so on and so on and so on. We complete that, and then we join the dots. These ones are easy, I said. How come? Well, there's nothing to add to it, right? All you got is one wave, so all you got to do for this one is trace the path. So you do that through the entire 2 waves, get the interference pattern. Because it produces a bigger wave, we call it constructive interference. This one, on the other hand, it's the middle part. Once again, that's the hard part because it's the part that's overlapping. We'd say 2 above, 1 below gives me about +1. 2 above, 2 below gives me 0. 2 above, 2.5 below gives me -0.5. And then again, these ones are easy. So we start joining the dots, joining the X's together, and we keep going for the rest of the waves, and we get, what kind of interference was it again? JC, what was it? Destructive interference, because we're producing a smaller wave. Not complete destructive interference, but still destructive interference. All right? And finally, we showed you constructive and destructive interference where we had 2-point sources. It's like saying you got two fingers, you're dipping them into water like this, dip, 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 and you're making these constant circular waves that are emanating out or radiating out from around these two sources in the water, and it's producing these two circular waves. And in between, in the middle, we get some interfering taking place. Yesterday, we traced through all these. We saw that when we had a crest meeting a crest, we got a bigger crest. Trough meets a trough, we get a bigger trough. And we ended up getting the pattern that was formed ended up looking something like this. These lines of constructive interference. Like this. But then we had these lines of destructive interference as well in between them. I won't go through the analysis of where these lines came from again. Okay, you'll remember that, right? When crest meets crest, when trough meets trough, we got constructive. Crest meets trough, we got destructive. What's another name for these lines of constructive interference here? Yep. Antinodal lines, good. And these lines of destructive interference, another name for them is? Jacob, what do you think for that one? If these constructive interference lines are called antinodal lines, then these destructive interference lines are called nodal lines, good. This would be the kind of thing where if you're on an air mattress in the water right here, you're going to be bobbing up and down like crazy because the crests are twice as big and the troughs are twice as big. But if you're on the air mattress right here, then you're going to be just enjoying the sun at rest because it's complete destructive interference and there's not going to be any waves, period. These happen to be sound waves. You're generating a constant sound right here and a constant sound of the same frequency right here. Then you're going to get a line right here and here and here where the sound seems to be twice as loud. But you're going to get an area right here and here where, what would you hear if you were standing right here? Nothing, because it would be destructive interference. So really loud, quiet, really loud, quiet, and so on. Okay? Now, dealing with sound, it's kind of tricky to make that happen, right? Because when you're dealing with sound, usually we're dealing with changing frequencies. When I speak, when you speak, the frequency of your voice and of my voice changes somewhat. You can't do, you're not going to see this pattern in that case, right? Because it's assuming that you keep producing the same frequency. But if you had a constant frequency tone, like produced by a computer or some musical instrument, then that's what you'd hear. Or not hear, as the case may be. All right? Okay, we got a couple things that we're going to do today here. The first one is called diffraction. Diffraction, here we are. Diffraction is defined as the spreading out of a wave. Now let me draw a picture to help you to understand what I mean by that. If we've got a barrier, that's my barrier there, and there's an opening in that barrier, and waves, whether it's sound waves or light waves or water waves, whatever the case may be, waves are coming towards that barrier. You're going to find that most of the wave ends up reflecting, right? It hits the barrier, the concrete barrier or whatever, and reflects back to where it came from. And then you're going to find some interference over here, right? Like this part of the wave right here reflects off of this boundary, comes back here, and it's going to interfere with the waves that are still coming towards the barrier. But that's not what I want to look at right now. I want to look at the portion of the wave that goes through the opening. There's only that small portion of the wave that goes through the opening, right? But that small portion that does go through the opening ends up spreading out like this. That's called diffraction, the spreading out of a wave. It's not bending, it's not changing direction, it's just spreading out. If my classroom door is open right now, if you were to go down the hallway, you would still hear me somewhat. And the reason you would hear me somewhat is because the sound that's coming from my voice goes through the opening in the doorway, and it would diffract outwards. It would spread out as it went outwards. Now, depending upon the size of the doorway, depending upon the frequency and the wavelength of my voice, the amount of diffraction might be more or less, but you're still going to get some spreading out. Otherwise, you wouldn't hear me. If you go down the hallway, you wouldn't hear me if there was no diffraction taking place. There's three factors that we want to look at here in order to determine which one, what's going to cause more diffraction, more spreading out. If the size of the opening is small, then the amount of diffraction will increase. So if you decrease the size of the opening, then the amount of diffraction will increase. So this opening up here, okay, if I make that smaller than it is right now, the waves are going to spread out even more than they're spreading out right now. The frequency of the wave, I don't know, I don't find too much trouble remembering that one, right? If I make it smaller, okay, it's more like, I make the size of the opening smaller like this, it's almost like you throw a rock into the water. When you throw a rock into the water, you get just circular waves produced. So it spreads out more than it spreads out when we have a bigger opening. Have a bigger opening, it's closer to just going straight through. This one, I always had trouble remembering this one though. How does frequency affect the amount of diffraction? The higher the frequency, the more or less diffraction takes place. You know what, when I was in high school, I always got this one mixed up. Even when I first started teaching, honestly, I would get this one mixed up. I just couldn't remember what it was. And then one day, it occurred to me. There was this way that just a light bulb went off that helped me to remember how frequency affects the amount of diffraction. So I'm going to tell you a quick little story that helps me remember how frequency affects the amount of diffraction. It may not help you because it's a story that happened to me. The more meaningful a story is to you, the more likely you are to remember it. So if you have trouble remembering this or something like this, like come up with your own story. Don't steal mine. Come up with your own story if you're having trouble. But if mine helps you, then so much the better. When I moved to Alberta, I lived in, I don't know if you guys know where these are or not. There's these brown apartment buildings that are just at the base of the hill under OJ, Okotoks Junior High School. You know what I'm talking about? You guys know what it's called? Wedgwood Greens, behind the courthouse. Okay. That's where, back when I moved to Alberta 23 years ago, that's where every teacher that came to Okotoks lived, because that was the only set of apartments in Okotoks when it was 7,000 people here. Everybody lived there. And I remember when I first started teaching here, I remember I would go to bed at like 11 o'clock or whatever, and I would listen to this radio show on AM radio. And I liked to listen to this radio show. I'd set the sleep timer on my radio, and it would to an hour, and it would turn off in an hour automatically. And that's how I fell asleep. I always like to fall asleep to voices, like to talking going on, to background noise going on. And it worked. It worked well. And then one night, I turn on my radio, and it's like something different on there. It's not my radio show. It's not the show that I like to listen to. This silly call-in show that I would always listen to, where people would call for advice. Like, to me, like, if you call a radio show for advice, like, your issues are bigger than the issues that you're discussing. Like, there's got to be a disorder that you have that would cause you to call a public radio show and discuss your problem. But anyways, yeah, that's what I would listen to, and I would be entertained by this. But it was gone one night. I couldn't find it. Like, how am I going to fall asleep now? I can't listen to my radio show. So for a couple of weeks, I was like, I can't sleep. Eventually, I'd go to sleep, but had a harder time going to sleep. And then one night, I was driving home from school. I'd been at school late, and I was driving home from school at 10 or 11 o'clock at night. And I got the radio on some other station, just like want to listen to something else. And there's my radio show. It's on a different station. It's on an FM station. So I'm listening to AM, can't hear my radio show anymore, but FM, it's on there. So I go home to my apartment, and I tune my radio to this FM station because I figure, all right, perfect. I'm going to go to sleep listening to my radio show. I'm going to get back into my routine. Couldn't hear it. My FM radio station was completely snow. It was snow noise, random noise in my apartment. But yet, in my car, on the other side of town, because my school, Holy Trinity, used to be on the other side of town, right, where JP2 is now, I could hear it no problem. But when I got to my apartment, I couldn't hear it on this FM station. Okay, the FM station was snow. Here's what was happening. Okay, if this is my apartment at the base of the hill, and these are the radio waves, the AM radio waves, this is what I could hear. The only problem was my radio show wasn't on AM radio anymore. Okay, the AM radio waves, okay, went over the hill, and then they diffracted, or they spread out like this. But when I tuned in FM, the FM radio waves, which have a higher frequency, by the way, you don't see this on radios as much now because it's all electronic tuning, but you used to see, it used to be labeled on a radio, AM or FM, and it used to say for AM, kilohertz or thousands of hertz, FM, megahertz or millions of hertz. FM is million hertz, AM is 1,000 hertz. So FM is higher frequency. In other words, the waves are closer together. Here's FM, where the waves are closer together. Those FM radio waves go over the edge of the hill, and they spread out as well. But they don't spread out as much as the AM radio waves do. They diffract, but not as much. So, what can I hear in my apartment? I can hear AM because AM has a low frequency, and low frequency diffracts more than high frequency. As the frequency goes down, the amount of diffraction goes up. If I'm listening to my FM, which is higher frequency, then you can see that it diffracts less, and that's why I couldn't hear it at the base of the hill. Now, why could I hear that FM station on the other side of town when I was leaving school? Here's my car as I'm driving home from school. I'm on the other side of town. The FM radio waves had no problem diffracting and reaching the bottom of the hill by the time they got to the other side of town. They just weren't diffracting enough or quick enough to go through my bedroom in my apartment at the base of the hill. Does that make sense? So lower frequency, small frequency, AM radio diffracts more than higher frequency than FM radio. Now, I always had trouble remembering wavelength as well, how that was affected, or how that affected the diffraction as well. But the good news is, if you can remember frequency, then wavelength is just the opposite. As frequency goes up, wavelength goes down. So we would say that if you decrease the wavelength, then what effect is that going to have on diffraction? the amount of diffraction or the spreading out will go down. Because it's the opposite effect of doing something on frequency. So this one, never had any trouble remembering that one. For whatever reason, the opening gets smaller, it becomes closer to being a full circle. More diffraction occurs. Okay, I just know that one. But this one, still to this day, I got to think about it. Whenever I'm doing it, I got to think about how the frequency affects it. And the way that I think about it is to remember, okay, I could hear AM, low frequency at the bottom of the hill. I could not hear FM, or high frequency, at the bottom of the hill. So AM must diffract more.